Hey friends, welcome to my video on busbar sizing. An electrical busbar is defined as a conductor or a group of conductors used for collecting electrical power from the incoming feeders and distributing them to the outgoing feeders. Materials generally used for busbars are copper and aluminium. Copper has better conductivity, high tensile strength, and is more ductile than aluminium. However, copper has higher density, which results in higher weight. Now let us understand why is it important to size a busbar correctly. Well, an undersized busbar will result in excessive heating of the busbar under normal operating condition, leading to rise of temperature beyond permissible limits. While an oversized busbar will lead to a costly switchboard. And the major factors affecting busbar sizing are voltage and current rating of the system, enclosure ingress protection rating, whether the panel is provided with forced ventilation or natural ventilation, working and ambient temperatures, heat loss by convection and radiation, heat generated in the busbars. Let us now understand how electrical busbar current rating is defined. Busbar current rating is normally defined as below: continuous current rating and short circuit current rating. Continuous current rating is the amperes that a busbar will carry continuously in free air without exceeding the temperature limits. Continuous current rating is expressed in amperes. Whereas the short circuit current rating is the maximum current a busbar can safely withstand for a specified time, such as 1 second or 3 seconds. Short circuit current rating is expressed in kiloamps per second. Let us now see how to size a typical busbar. Let us consider that we have a 6.6 kV switchboard busbar fed from a 33 by 6.6 kV 25 MVA transformer, for which we need to find out the current rating. The transformer secondary current is calculated as MVA into 1000 divided by root 3 into kV. By incorporating the transformer MVA and the voltage values, the transformer secondary current is calculated as 25 MVA into 1000 divided by root 3 into 6.6, which is equal to 2187 amps. Hence, the manufacturer's next standard busbar rating of 2500 amps may be selected for this example. Let us consider a different example where a 11 kV switchboard busbar is fed by two numbers 33 by 11 kV 20 MVA transformers. In this example, the transformer secondary current works out as 1050 amps. Hence, the secondary current from two transformers is equal to 2100 amps. Accordingly, the manufacturer's next higher standard busbar rating of 2500 amps is selected. After calculating the continuous current rating of the busbar, we now need to calculate the short circuit current rating. There are two approaches to calculating the short circuit current rating. In the first approach, we calculate the maximum fault current the transformer will let through. While in the second approach, we calculate the fault current considering the available fault current of the power system upstream to the transformer. In the first approach, it is considered as if the power generation system is directly connected to the primary side of the transformer. This is also referred to as infinite bus calculation. This will result in the maximum fault current the transformer can supply the bus bar, and any other impedances are ignored or considered equal to zero except the transformer impedance. What this really means is that the secondary of the transformer will never see a current greater than what has been calculated by this method. Any change in the power system upstream to the transformer is not going to increase this maximum fault current. This method is a shortcut method and conservative on the side of safety. While the infinite bus approach is a quick and simple method to arrive at the maximum short circuit rating of a bus bar, it overlooks some very important factors. Decrease in short circuit current due to source and line impedances, short circuit currents contributed by the motors. In case the short circuit current calculation is being used for arc flash study, then we cannot ignore the lower short circuit current. During an arc flash, a smaller short circuit current may cause the upstream protective device to take longer to operate, leading to a greater overall incident energy and a greater hazard. Also, when a new or existing equipment cannot handle the conservatively high available fault current as calculated through the infinite bus method, further detailed analysis needs to be conducted so that the equipment could be sized appropriately. Therefore, in the second approach, all impedances as well as the motor short circuit current contributions are considered to arrive at a very accurate short circuit current rating. Let us now calculate short circuit current rating of a bus bar. For the ease of understanding, we will use the infinite bus method for calculating the short circuit current. Short circuit current is calculated as transformer kVA into 100 divided by root 3 into secondary kV into transformer impedance. Using the above formula, the maximum fault current the transformer in our example will let through is calculated as 25,000 into 100 divided by root 3 into 6.6 into 10, considering transformer impedance is equal to 10%. This results in a short circuit current of 21869 amps. This means that the secondary of the transformer will never see a fault current more than 21.869 kiloamps. Accordingly, the manufacturer's next higher short circuit current rating of 25 kiloamps is selected. Once the busbar rating is finalized, it is the responsibility of the panel manufacturer to decide the busbar size based on these ratings. The busbar cross-section is sized based on the Melson-Booth equation published in the Copper Development Association Review. The formula is as given below, where I is the permissible current flowing through the busbar in amps. Theta n is equal to the ambient temperature in degrees centigrade. Theta minus theta n is the permissible temperature rise. S is the busbar cross section in centimeters square. P is the busbar perimeter in centimeters. Rho 20 is the conductor resistivity at 20 degrees centigrade. Alpha is the temperature coefficient of resistivity, while K is the conditions coefficient, which is actually a product of 6 coefficients, K1 to K6, where coefficient K1 is a function of the number of busbar strips per phase. For single busbar, K1 is equal to 1, and for 2 or 3 bars, the table below can be utilized. Coefficient K2 is a function of surface condition of the busbars. For bare conductors, K2 is equal to 1, and for painted busbars, K2 is equal to 1.15. Coefficient K3 is a function of the position of the busbars. For edge-mounted busbars, K3 is equal to 1. For single busbar, which is base mounted, K3 is equal to 0.95. For several base mounted busbars, K3 is equal to 0.75. Coefficient K4 is a function of the place where the busbars are installed. For calm indoor atmosphere, K4 is equal to 1. For calm outdoor atmosphere, K4 is equal to 1.2, and for bus bars installed in non-ventilated ducting, K4 is equal to 0.8. Coefficient K5 is a function of the artificial ventilation. Without artificial ventilation, K5 is equal to 0.9, and with artificial ventilation, K5 is equal to 1. Coefficient K6 is a function of the type of current. For alternating currents of frequency less than equal to 60 Hz, K6 is a function of the number of bus bars per phase and of their spacing. The value of K6 for a spacing equal to the thickness of bus bars can be taken from the table below. Let us now try to work out the size for 2500 amps bus bar using the Melson-Booth equation. Let us consider 2 into 120 into 10 mm bus bars per phase and check its adequacy to carry 2500 amps. Theta n, the ambient temperature, for our example, let us consider equal to 40 degrees centigrade. As per IC 60694, for bolt connected bare bus bar, the maximum temperature is permitted is 90 degrees centigrade. Therefore, the permissible temperature rise theta minus theta n is equal to 50 degrees C. Is the bus bar cross section equal to 12 centimeters square. P, the bus bar perimeter, is equal to 26 centimeters. Rho 20, which is the conductor resistivity at 20 degrees centigrade, is equal to 1.83 micro ohm centimeter. The temperature coefficient of resistivity alpha is equal to 0.004. Let us now try to calculate the value of K. In our example, K1 is equal to 1.83 as we have two bus bars and the E by A ratio is equal to 0.12. K2 is equal to 1 as the bus bars in our example are bare bus bars. K3 is equal to 1 as we have edge mounted bus bars. K4 is equal to 0.8 as in our example the ducts are non-ventilated. K5 is equal to 0.9 as the example is without artificial ventilation. And as the frequency is 50 Hz and n equal to 1, therefore the K6 is equal to 1. Therefore, K works out as 1.3176. Replacing these values in the Melson-Booth equation, we have I equal to 2877 amps. Hence the selected solution of 2 into 120 mm into 10 mm bus bar is adequate as it is capable of carrying 2877 amps, which is greater than the required continuous current rating of 2500 amps. This concludes my video on busbar sizing. Thanks for watching. I hope you enjoyed this video. If you would like to see more such videos on electrical topics, please subscribe to my channel and share with your friends and colleagues. Also, don't forget to click on the bell icon so that you don't miss out on anything.